Welcome to This Explainer. Today, we're doing something a little different. We're going to break down the intensely microscopic world of chemical bonding, and we're going to do it in a very simple, easy-to-grasp way. How? By looking at it through a lens every single one of us understands: relatable human relationships. Because honestly, just like us, atoms are out there looking for their perfect match, awkwardly navigating personal space, and really just trying to build something stable. Let's dive in.
You know that old saying, sharing is caring? Well, one of our source materials uses this exact phrase to brilliantly describe the fundamental motivation behind atomic interactions. Atoms, much like people, really don't like being totally alone. They're constantly seeking stability. They want to feel complete. And to get there, they form cooperative alliances. It truly is all about finding a partner to share the load with, creating a mutual bond where both parties end up so much better off than they were on their own.
So why do atoms actually go through all this trouble in the first place? What's the end game? In a word, stability. In the atomic world, ultimate stability means getting a perfectly full outer shell of electrons. Chemists call this the noble gas configuration. You can absolutely think of this as the atomic version of a happily ever after. And to reach this incredibly stable state, atoms are willing to give, take, or share their outer electrons with whoever can help them get there. Now, how they actually pull off this stability depends entirely on the kind of relationship they build. And this perfectly illustrates our two main pathways: ionic bonds and covalent bonds. Think of an ionic bond like a complete transfer. Imagine you're wearing a thick, warm jacket, and your friend is freezing. You just give them the jacket completely. One atom gives away an electron, the other takes it, and those resulting opposite charges lock them tightly together. A covalent bond, on the other hand, is mutual sharing. It's exactly like two friends sharing a single umbrella in the pouring rain. Neither of you owns the umbrella completely, but by staying close and sharing it, you both stay dry, comfortable, and stable. As you can see right here, on one side we've got a classic ionic bond forming between sodium and chlorine. Sodium is essentially just handing its electron over to chlorine, which results in this perfectly ordered crystal lattice of positive and negative charges. It's a total, complete transfer. But on the flip side, we see covalent bonding in action. Atoms like nitrogen and carbon are mutually sharing pairs of electrons right in the dead center between them. It's this beautifully balanced partnership where those shared electrons act as the literal glue holding the whole relationship together.
But hey, just because atoms get into a committed relationship doesn't mean they don't have boundaries, right? In fact, what happens once they're bonded is fascinating. Just like human partnerships, these atoms suddenly find themselves aggressively negotiating for personal space. In chemistry, this entire concept of boundary setting and spatial arrangement is governed by something called VSEPR theory. Now, don't let the acronym intimidate you. We are definitely going to keep this simple. This boundary setting process stands for the valence shell electron pair repulsion theory. Stripped down to its basics, it simply means that electron pairs clustered around a central atom will arrange themselves to be as physically far apart from each other as possible just to minimize repulsion. Since all electrons have a negative charge, they naturally repel one another. You can think of these electron pairs as roommates sharing a very tiny apartment. They want to stay together under one roof, sure, but they are absolutely going to push their beds into the exact opposite corners of the room just to get some breathing space. Now, this is where it gets really interesting. We have this concept of lone pairs. Not all electron pairs are actively shared between two atoms. Some just kind of sit on the central atom by themselves. And these non-bonding lone pairs act a lot like really needy roommates. Because they aren't stretched out between two atoms, they fan out, take up extra room, and effectively squish the other bonded atoms closer together. In methane, there are no lone pairs, so all the bonds are perfectly equally spaced. But you add one lone pair in ammonia, and it immediately pushes the bonded atoms a little closer. Add two lone pairs, like we see in water, and those bonded atoms get squeezed together even tighter. And you can see the literal visual evidence of this squeezing effect changing the geometry right here. Methane sits happily with this nice, wide bond angle of 109 degrees in 28 minutes. But as we move over to ammonia, that invisible lone pair pushes the angle down to 107 degrees. Finally, look at water on the right. Those two demanding lone pairs squeeze the hydrogen bonds all the way down to just 104.5 degrees. It's such a perfect representation of how these invisible repulsions physically shape the molecules we rely on every single day. But as anyone who has ever been in a relationship knows, things aren't always just about simple personal space or couch real estate. Sometimes merging two lives, or in this case two atoms, completely changes the fundamental identity of both parties. So what actually happens when atomic relationships get truly complicated? Well,
we have to upgrade our simple diagrams to something far more advanced, molecular orbital theory.
Take a look at this diagram mapping out molecular orbital theory. This represents the ultimate relationship merger. Instead of just sharing an umbrella, these atoms are completely fusing their individual spaces to form entirely new molecular spaces or orbitals with wildly varying energy levels. As you can see by the complex stacking here, the original atomic identities are just gone. They've combined forces to create a much larger, completely unified molecular system.
To keep this complex theory simple and super easy to digest, I've broken it down into a quick table. Basically, think of molecular orbital theory as a rigorous relationship health check. We calculate a value called bond order. To do this, we tally up the bonding electrons. These are the positive forces keeping the relationship together, the ones stabilizing the molecule. But then we also have to count the anti-bonding electrons. These are the hidden tensions, the potential reasons for a breakup, which actively destabilize things. By subtracting those anti-bonding forces from the bonding forces, we get the bond order. And that number tells us the overall health and net strength of that bond. Which brings us to this massive deal breaker of a number: 0. If you do this calculation, weighing the stabilizing forces against the disruptive ones, and your calculated bond order comes out to exactly 0, well, the molecule simply doesn't exist. The destabilizing forces completely canceled out the stabilizing ones. It means the partnership failed before it even had a chance to begin. It's basically nature's way of saying these two atoms are absolutely, positively better off staying single. Up until now, we've been talking about these intense, highly committed, life-altering bonds. But we really can't ignore what sociologists and chemists call the power of weak ties, because not every interaction needs to be a lifelong commitment to have a massive impact. In the chemical world, there are temporary, much weaker forces that profoundly shape the physical matter around us. They literally dictate whether something is a solid, a liquid, or a gas at room temperature. A perfect, vital example of this is hydrogen bonding. As mapped out here, a hydrogen atom that is already bonded to a highly electronegative atom, like oxygen, can actually form a secondary weak bridge to a neighboring molecule. It's not a full covalent or ionic bond, not even close, but it is a remarkably strong attraction between different molecules. This specific intermolecular force is exactly why water molecules stick together the way they do. It gives water its uniquely high boiling point and, honestly, makes all life on Earth possible. So, to wrap up our journey through these chemical relationships, let's quickly recap the hierarchy of bond strengths. At the very top, we have ionic bonds, the strongest, most intensely electrostatic commitments, where electrons are fully transferred. Right below that are covalent bonds, those incredibly strong mutual sharing partnerships. Then we step down to our weaker ties, hydrogen bonds, which act more like strong acquaintances holding separate molecules together. And finally, at the very bottom, we have van der Waals forces, like London dispersion forces. These are so weak and fleeting, they're essentially the chemical equivalent of two people just making eye contact while passing in a hallway. We've seen how atoms seek stability, negotiate their space, and balance these massive forces of attraction and repulsion to literally create the universe as we know it. So I want to leave you with one final provocative thought. If all physical matter is really just a vast, complex collection of these incredibly diverse atomic partnerships working perfectly together, what kind of bonds are holding you together? Thank you so much for joining me for this explainer. I hope you found this incredibly illuminating and that keeping it simple made it click. Keep questioning, keep learning, and I'll see you next time.